All right, let's take a look at 2017 E&M number 2. This one is a circuit with a battery switch and then immediately a junction to have a capacitor and resistor in parallel with a resistor. Now they tell us that the switch is initially open and the capacitor is initially uncharged. This means that at the beginning, the capacitor acts like a wire. So we have resistor 1 and resistor 2 in parallel with each other. As the capacitor charges up and gets charge on it, and therefore a voltage across it, the relative currents are going to change, and we're going to end up with the battery supplying current just to R2 as the current is cut off in the capacitor branch. Now let's take a look at part A. They told us as we close the switch, the charge was 0, and the charge is going to build up to be some maximum value, and it's going to do so asymptotically. And the maximum charge is going to be a result of the maximum voltage, because if you remember, Q equals VC, and we need to figure out what the voltage is going to be across a capacitor. Well, if you take a look at our circuit here, the positive side of the capacitor is attached to the positive side of the battery, and then the negative side of the capacitor is attached through a resistor also to the negative side of the battery. There is nothing in this loop outside of the branch that contains both the capacitor and the resistor. There's no extra resistor up here with the switch or down here. So as the current goes to 0, that means the voltage drop across the resistor will go to 0, and all of the voltage drop in this circuit, in this branch, will be on the capacitor. So for this branch and that capacitor, the maximum charge on there is going to be the battery voltage times the capacitance. So this Y value on the Q axis here is going to be V0 times C, and it's going to reach the curve as a function of time is going to look as an exponential decay that's upside down, and that shouldn't have a loop there. That's bother. Let's try this again. My drawing is not the best with this, so we're going to increase asymptotically. There's no S curve here. This is just an upside down exponential decay. Now, for part B, the currents through the two resistors. They told us up above that resistor 2 is less than resistor 1. Since these guys are in parallel, what that tells us is that the current through resistor 2 is going to be bigger than the current through resistor 1. As the current goes past the switch, it's going to split. Part of it is going to go through the capacitor, and part of it is going to go through the resistor. Now, since they told us that resistor 2 is less than, and therefore it's going to have more current, on this current here, we're going to have a dot to represent I2, and then we're going to have a dot to represent I1, and then if we add these two guys up, we're going to get the total current. So this I is going to represent the steady state total current, and these two dots that I'm going to reposition just for the sake of drawing my currents so you can see the curve. So I'm going to exaggerate this, but they should be headed towards the top. So I1 is going to be lower, and I2 is going to be above it. And as we discussed up here, as the charge builds up on the capacitor, that means the current is going to be cut off from the resistor. So I1, which is in series with the capacitor, is going to have an exponential decay. Now, I1 plus I2 needs to be equal to the total current, which is represented by the dotted asymptote up there. So if we subtract these guys, we have the asymptote minus I1, we will get the upside down exponential decay curve. indicating that in the end, all of the current is going through resistor R2. And this is because the capacitor gets all charged up and no more current can go through that branch. Down in part C, they start to give us numbers. And they talk about how much time it takes to charge versus discharge. The amount of time that it takes to charge versus discharge is represented by the time constant. Now this R is the resistor that happens to be in series with the capacitor. For charging, resistor 2 is in parallel. It's not included in this time constant. It's resistor 1 that is included there. So for charging, we're going to have R1 times the capacitor. And when you plug in numbers, you're going to get 0.012 seconds for the time constant. Now this is not, what they're talking about here is 50%. This is not 50% of the time. This is simply a measure of how quickly the capacitor is going to charge up. And what we can do is compare that to how quickly is the capacitor going to discharge. Now when we discharge and we open this switch here so our circuit changes, our circuit effectively will be the capacitor becomes a battery, sends current through R2, sends current through R1, and then comes around to the negative side of the battery. This indicates that R1 and R2 are in series, and that should be a C there. So once you add in R2 to the time constant, you're going to get a discharging time constant of 0.02 seconds. Now, since it takes longer to discharge than it took to charge, this should indicate that it also takes longer to do 50% of discharge than it took to do 50% of charging. So delta TC is going to be less than delta TD, even though we didn't actually find what that time was. What we did was we found something that was related to it. Whatever the charging time is, it's going to be related to delta TC. Whatever the discharging time is, it's going to be related to delta TD. And since the charging time constant is less, that means the charging time is also going to be less. So you should check that point, and then you can use calculating the time constant to be your explanation for what's going on there and your justification of your answer. Now we'll scroll down and take a look at parts D and E. All right, immediately after the switch is reopened, so we've left the switch closed for a long time. Now the capacitor is charged up, and it has been charged up to voltage V0. And now we open the switch and remove the battery from the circuit. So the circuit is the capacitor, which acts like a battery, resistor 2, and then resistor 1. So let's calculate the current through resistor 2. So resistor 1 and resistor 2 are in series. So resistance total is going to be R1 plus R2. And the current total is going to be also the same as the current through I2. Every charge that goes through R2 also has to go through R1. And by Ohm's law, current I total is going to be the total voltage divided by the total resistance. Total voltage is going to be V0, and the total resistance is going to be R1 plus R2. And when you plug in numbers, you should get a current of 6 milliamps, or 0.006 amps. That's D part 1. D part 2. Is the current through the resistor increasing, decreasing, or constant? So as soon as we open the switch, the first charge jumps off the capacitor and runs around. The second one jumps off a little bit more slowly, and the capacitor will be discharging according to a previously derived equation that is exponential decay. Remember that current is the derivative of charge as a function of time. So if you take the derivative of an exponential decay, you get the same thing times a constant, and this constant is going to be V0 over R1 plus R2 for the initial current. But then, as soon as that clock starts ticking, T increases. That means this whole term starts getting smaller, and that means the current is going to be getting smaller. So we would say that this guy is decreasing, and it is an exponential decay. And you can use your justification for your answer, the fact that the capacitor is going to be discharging at an exponential decay rate, and the current is a derivative of that, which gives us another exponential decay. All right, E part 1. The energy stored in the capacitor. The energy stored in the capacitor is 1/2 CV squared. And the instant after the switch is opened, it's still got voltage V0. When you plug in numbers, you should get 9 times 10 to the minus 5th joules, which we could turn into microjoules by moving the decimal point over 1, and we get 90 microjoules, because then that becomes times 10 to the minus 6th. For part 2, the energy dissipated by the resistor. All right, energy dissipation is related to power dissipation. So power is going to be I squared R, and power, so that's 1 and 1 and 1, and power 2 is going to be I2 squared R2. But remember, way back up here in part D part 1, the I total is going to be the same as I2, which is also going to be the same as I1. So these two currents are the same, and these two resistances, that's where the difference comes in. Now the question said the energy dissipated. Well, energy dissipated, we just need to multiply this guy by time to go to energy. So if we multiply this guy by time, that's the energy dissipated by 1, and that's the energy dissipated by 2. Now here again, the time is going to be the same. However long the current is going through R2, it's also going to be going through R1. So we can divide these guys, each of them, by the total, and we have the total amount of energy. That was E part 1. So energy dissipated by, they wanted 1. It's going to be just a fraction, because keep in mind, the only difference between these guys is in the resistance. So it's going to be R1 over the total, because we don't want the relative values. What we want is how much of the total do we have, times however much was in the capacitor, which supplied all of the energy. So U1, E and U energy 1, or U, it doesn't really matter, it'll be the same thing. R1 is going to be, what did they tell us? 150. So 150 over the total resistance, which is 250, times the amount of energy that was put into the capacitor. Well, that's going to be 3/5 of the total. So 3/5 of 90 gets us 54 microjoules.